Hi, welcome to es201 Computer Techniques. This is week 6 and this is the lab introduction, and the topic this week is functions. So there are two lab assignments. Notice that there are two chapters in the Zybook, chapters 6 and 7. The first deals with functions, and then we talk about recursive functions, which are a particular type. So first let me talk about the lab that is in part 6, chapter 6. And this is working with functions, and in this lab you're going to write two versions of a function, making it an overloaded function. So first of all, what's included with the lab is a data file of temperatures, and so I kind of showed just the first few over here on the top. This file is included in the Zybook, but there's actually, this is hourly data for an entire year. So if you think about that, that's 24 hours in a day, 365 days in a year. So this has 8,760 data points in it. What you're going to do in this lab is you're actually going to determine what's called the average daily temperature change. And so let me explain what that is. So imagine that I just took one day, so if I have 24 data points right over here, so this would be the hourly temperature data for some particular day. And if I was to plot it, you would see it kind of has some minimum over here early in the morning, and then it heats up during the day, etc. The temperature change for this particular day, you take the maximum temperature at any point, the minimum temperature at any point, and then you take the difference between them. So that's what we're going to call over here delta T max, and it's actually what it changes. It's pretty much, you can think of it as kind of like the range, but it's actually the maximum minus the minimum. And then what you need to do is find out what the average of that is over several days. So that's simply the average will be, you're going to find all the delta T maxes for all the days, and then you just simply divide by the number of days in that range. Now your function is going to take a different range of days, and so for each day it's going to have to find the delta T max, and then it's going to go ahead and take the average of all of those. You're going to be writing an overloaded function. It's going to be able to call this various ways. And so the function that you're going to be writing is called mean daily temperature change, and it takes a couple different parameter lists. So the one I show over here, it takes data. This is actually loaded in the template file already for you. This will be the 8760 days, and this is a vector. And then the next two parameters are the first day and then the last day. And so this means you want the average over days 1, 2, and 3. So that's going to be inclusive. And so these are given what's called Julian days, which means a day counting starting at January 1 is day 1, January 2 is day 2, etc. And December 31st would be day 365. So this would be looking at a range of January 1st to January 3rd. Your mean daily temperature change, it will do all this math we just talked about. You'll be developing that algorithm, and then you're going to go ahead and just have a single return value that you can then be written to the screen. So just a kind of another example, again, if I call this from parameters 100 to 300, and again, remember those are Julian days, and so that would be, for example, April 10th to September 27th. There's another way you could write this, so you're actually going to write two versions of the function. You're going to be overloading it. Is instead of providing 3 parameters, you provide 2. You provide the data and then a single enumeration that you're going to define. That enumeration will be the month as a 3-letter abbreviation like this. At this point, your program will have to determine what are the Julian days for February, and then go ahead and determine that. So for example, February, this would be February 1st to February 28th. This is not a leap year, so you don't need to worry about that in this program. Then this program, once it determines those, is it's actually going to call the other function that you wrote, and it's going to call 32 and 59. So this function, the one over here that has this form, calls the other form. And the reason you want to do this, that way you only have to write this function once, and if you were to modify that function, you only modify it once. So this function is going to be calling the other version of the function to do it. So all the second version of the functions we're doing is determining what these particular values are. All right. Now the second program, this is in chapter 7, this is writing a recursive function. We're going to be doing something that's kind of interesting. We're going to be working with blockchain basis of this, and so what the program's actually going to do is you're going to be writing a recursive function. It's going to create what's called a Merkle tree of hash functions. So I want to spend a little time explaining what those are, and also just kind of giving the context of why this is important, or what I find at least interesting, if not necessarily important. So we're going to be writing a foundation of blockchain, and blockchain is a foundation in Bitcoin, and you've probably, I'm sure, heard of Bitcoin. I'll just kind of give you a little bit of background if you're not particularly familiar with Bitcoin. Bitcoin's called a virtual decentralized cryptocurrency, and let me define what those things mean. Here's a definition from the ECB, the European Central Bank. Virtual is a type of unregulated digital money issued and controlled by its developers and used and accepted by the members of this virtual community. That means there's no government that's actually issuing this or taking care of it or even watching over what happens. So decentralized, as I said, means there's no central or controlling power or entity. And so agreement is really just by a majority of the users agree, yep, that sounds like a good way that this currency could be used. The last thing Bitcoin is called a cryptocurrency, and most of these virtual currencies are cryptocurrencies, and that means the medium of exchange uses cryptography to secure your transactions and to maintain pseudonymity and anonymity. Sometimes people think this is a positive, some people think this is a negative, but it's a feature of Bitcoin. It's actually a feature of most virtual currencies. Just a little about Bitcoin. It actually was created by this person called Satoshi Nakamoto in 2008. They wrote an online paper for it. No one actually knows who Satoshi is. No one has actually stepped forward and said they were. This was just published on the web. It could be a group of people. It could be a person. No one really knows. It's sort of an interesting feature of Bitcoin. What you're going to be working with is blockchain, which is a foundation of Bitcoin. And blockchain is actually a foundation of a lot of different currencies. And in fact, you've probably in the recent years heard about Libra. This is a cryptocurrency being pushed by Facebook that they're working on develop. There's another very common one that's called Ethereum, or Ether is the name of the actual currency. These are two different versions. They both use blockchain as well. So it's not limited to just Bitcoin. And in fact, there's a lot of non-currencies. There's something called Ripple, which actually deals with shipping transactions. And a lot of publicly traded large banks actually use blockchain as well. So I don't want to mention that it's limited to just Bitcoin, but Bitcoin's sort of the one that made blockchain initially famous. Just a little bit more about background of Bitcoin, which was why I think it's interesting. Here I'm showing a plot of what the price of Bitcoin is in dollars. This is how much each Bitcoin is worth from about 2014 to just yesterday when I pulled this off of the web. And if you look down here on 2014, the scale over here is this is $15,000. Didn't really register much at all. And then you look around 2018, it spiked. It was almost $20,000 per Bitcoin. And then you can see since then it has been incredibly volatile. If you were to compare this to any other type of currency valuation, this is incredibly volatile. So again, some people find this interesting. Some people make it don't see it as a positive, but just makes a fairly dynamic currency. So I want to talk about blockchain. This is an element of Bitcoin, and this is the interesting part, and this is where Merkle trees come in and hash functions. So first of all, let me talk about a blockchain. And so a blockchain is what's called a public append-only ledger, and it records all your transactions ever made. And this is why it's a foundation for a decentralized currency that there's not a controlling feature of. So the idea is you might have a series of transactions. And transactions is just any time one person or group of people pays somebody else a certain amount. That would be called a transaction. And so what you do is you want to go ahead and record all what those transactions are, and it just gets larger and larger. Append only, meaning that you never go ahead and erase or change anything. You just keep writing all the transactions that ever occurred. And so you have this listing of every transaction that ever occurred within Bitcoin. The reason that is important is because anytime you want to prove that somebody has a Bitcoin, since there's not physical Bitcoins, how do you know it? Is that you have to go back and traverse this entire ledger and find out, make sure that the person that says they have a Bitcoin actually does have a Bitcoin. And that's why it's important that it's append only and you never delete anything from it. So here's kind of an example. Imagine today Alice wants to pay Bob 2 Bitcoins. And before we can do that, we all need to agree that Alice has 2 Bitcoins to give Bob. And in order to do that, we read back through the ledger, and at some point we see, hey, Carl gave Alice 5 Bitcoins, so she obviously must have had 5 Bitcoins, but that's all under the assumption that Carl had Bitcoins to give. So you keep reading back through the ledger. Maybe at some point you see that Carl got 4 over here, and he got another 3 over here, so then he did have those in order to give those to Alice eventually. And you can imagine this just keeps going on and on and on, all the way through the ledger, all the way to the very beginning of the Bitcoin history. And so this is pretty laborious, you could imagine, to do. And so it would be a nice way to speed it up. And that's where this idea of hashing Merkle, a Merkle tree of hash functions comes in. So let me talk first about hash functions, and primarily what are called cryptographic hash functions. So a hash function is something that takes an arbitrary sized input and turns it into a fixed size output. And it's cryptographic means that it's pretty much impossible to invert it. So here's kind of the idea. A hash function takes a whole bunch of bits, right over here. I'm just showing you this number of bits, and turns it into something else. So it sort of just mixes them all up in some way. It takes an arbitrary sized, so right over here I show a smaller number of bits, only 3, and every time it's going to turn into a number of bits, but they're of the same length. And so here I show a whole bunch of bits. This is my arbitrary sized input on the left-hand side, but notice how it's always turning into the same number of bits on the right-hand side. So the idea is that you're to take an input, which is going to be, what we're going to be interested in are going to be text strings. They could represent like a transaction, like Bob paying Alice 2 bitcoins. It's going to go through this cryptographic hash function, and it's always going to produce essentially just a whole bunch of bits. And here we're showing it in hexadecimal just to make it a little bit shorter, because it turns out we're going to be working something that's got 256 bits, and so I don't have to keep writing 256 zeros and ones down here. The interesting thing about hash functions as well is that if you just make a teeniest change to the input, the output should look dramatically different. So notice here I've got the red fox jumps over the blue dog, and here's what my hash is. If I go ahead and just change one letter in over, I just go ahead and mistype maybe or put a V instead of a U, notice that the hash function looks dramatically different. Again, if I just make one little subtle change to it, the hash function changes a huge amount. This makes it really impossible to invert because it's really impossible to find any sort of trend, if you were to maybe look at examples, to determine what the input would be. Okay? So, looking at cryptographic hash functions, we want something that's called non-invertible. And that means that no two text strings could produce the same hash. Right? So, no two inputs would ever produce the same output. Okay? So, here's the idea. I've got all my arbitrary sized input. This would be all possible text strings of any number of bits, right? So this is obviously a very, very big thing. This is like every possible sentence that could ever be produced, every book, everything, etc. And then you're going to produce it just into n byte strings, and we're going to be looking at 256 because that's what we tend to use in these blockchains right now. And so this is obviously going to be much smaller because this is fixed at 256 bits, where this one over here can be any number of bits that you want at all. So something that's called a collision is if two plain text strings produce the same hash. So that says, for example, notice that this hash goes right over here and produces this hash. Imagine I had some other string and it happened to produce the exact same one. That would be called a collision. Now, if you realize if this is a much larger set than the one on the right, it seems like those have to exist. And in theory, they do. But in practice, it really almost never happens. And let me kind of demonstrate why that is. So we're going to be looking at 256-bit hashes, and I read it here as a hexadecimal, and so this is going to be 64 hexadecimal characters can represent 256 bits, because that's 16 to the 64 is the same as 2 to the 256. All right. So the number of different values you could have, this is the number of possible green values you can have. 2 to the 256 is this 1.158 times 10 to the 77th power. And that looks like a pretty big number. And let's put that into context of exactly how big that is. If we were to look at the number of seconds since the Big Bang, right, that is only 10 to the 17th. That is just a minuscule number relative to the number of different hashes there are. If you were to look at the number of grains of sand on the entire Earth, they estimate that at about 10 to the 21. We're still not even close to what that is. Here's the world's fastest supercomputer right now. This is Japan's Fugaku. This is actually running a bunch of COVID-19 tests right now as well. Anyway, this produces a floating point operation. That's what a flop is. And if this thing had existed since year 0 AD and been running since then at its maximum speed, it still would have only produced 9.2 times 10 to the 26th floating point operations. So we're still incredibly smaller to the number of different hashes. And in fact, the only way we can get close, if we look at what some astronomers are estimating, the number of atoms in the entire universe, they think that might be around 10 to the 80, and that's about the number of different 256-bit hashes. And that's why this is sort of the standard that's being used right now. So let's talk about how hashes fit into blockchains. Hashing simplifies verifying that blockchain. Remember, we have to read back through that whole ledger, and reading this huge ledger would take a long time. So what happens is you take a group of transactions, and then you go ahead and hash those. So this is just arbitrary sized input, and you're going to go ahead and produce a hash on the output. And here's the idea. As a blockchain is moving along, take a bunch of transactions, you produce a single hash. This is this large input, single hash, and then what you do is you keep appending that to the next set of transactions that occurs, and then you go ahead and produce another hash. So each time you're just kind of shuffling forward these hashes that are going to be these 256-bit things. This is sort of a recording of everything that's ever occurred before it. And so this one right over here records every transaction over here and every transaction over here, in addition to all the transactions that happened there. And you can keep representing it in a small amount. So that's what makes this a fairly efficient method. So here's how the Merkle tree fits into it. So a Merkle tree is what's called a binary hash tree, and it improves the efficiency. So binary means that if you take a bunch of inputs, you always pair them up to go ahead and give yourself an output. Merkle trees tend to be shown sort of upside down, where the root is at the top, but that's just kind of a consequence of the way they tend to be shown. Here's the idea. You have a bunch of lines of input or transactions or whatever showing over here on the bottom. So this might be line 1 and line 2. And the idea is you go ahead and you take a hash of those, and then you go ahead and concatenate them together, which just means you put one right after the other, and then you hash that. And you keep doing that in pairs until you end up with just one hash at the end, and that's called the Merkle root. The reason this is efficient is, so imagine I wanted to go ahead and verify this transaction right over here. This is what I wanted to find out. Bob gave Alice his 2 Bitcoins. I'm going to go ahead and need to hash this line of text here, but then all I need to do is actually know what these 2 hashes are right over here to verify that it actually exists. So I don't actually have to go back and read all those previous transactions. I actually now just need a list of 1 hash as I build my way up through the tree. And so it makes it a little bit easier to go ahead and verify transactions. And that's important because verification is just done by the general public out of the good of their heart. So, well, not entirely out of the good of their heart. They actually get a little bit of money for doing for it. And this is the way that it works. You need people to go back and get a bunch of people by consensus to say, yep, that was a valid transaction. And so the way this is done is that Bitcoin, this is the basis of it, it goes ahead and gives what are called rewards whenever you get people that can verify a transaction. And currently the reward is, this was actually just recently halved on May 11th this last year. It's 6.25 Bitcoins, which is still a lot of money. That's almost $66,000 each time you verify a block of transactions, not just one transaction, but a big block of them. And the reason this is nice and this is important is because to have a decentralized currency, you've got to have a consensus of a lot of people, because there's no central authority to go ahead and say, yes, that is a valid Bitcoin. So the way this is done is you go ahead and if you want to be what's called a Bitcoin miner, someone that's going to verify them, you take a whole bunch of transactions that are being broadcast on the network. Those are the purple ones. And then what you do is you create this transaction, this special one that just creates Bitcoin out of nothing. And it says that essentially Roy Peterson's going to go ahead and get 6.25 Bitcoins. You add that as a transaction, and then you go ahead and create a hash that you want to put onto the blockchain. Now, clearly, you can't just, anyone can do that just right away, the first person to do it, because people would be doing that all the time for the $66,000. And so we need to have some sort of way to restrict how often people get to do that. And we do that by looking for what's called the nonce, okay? And the idea is that you need to go ahead and reach a certain goal. So what you do is you take a bunch of transactions, all those purple ones, you add your red one on there, and then you go ahead and hash it down to that Merkle root. So we use that binary hash tree. But what you have to then do is add another 32 bits onto the end of it and take that hash. And this one right over here has to meet a certain metric. And what you need to do to want to meet that metric is you need to have a certain number of zeros at the bottom. It needs to be a certain number pretty low to the bottom. So you just keep guessing what this 32-bit nonce is until you actually end up with a bunch of zeros. If you're the first person to maybe get, say, 6 zeros in the front, then you actually go ahead and win. That means that your block of transactions with your red transaction gets put onto the blockchain, and then that's actually going to now give you 6.25 Bitcoins, and then people then move on, and they now have to work with the hash that you generated, and then create another group of transactions. And the way Bitcoin is set up is so that about every 10 minutes someone is able to verify a group of transactions. And so they go ahead and that goal determines how many zeros have to be in front of this, because it depends on how much power is actually on the network. And we talk about power. This is actually pretty lucrative. Here I show a picture of what's called a Bitcoin mining farm. These are all specialized computers. There's just racks and racks and racks of them. They're all trying to verify these transactions so they can go ahead and get that $66,000 bonus for verifying transactions. Kind of an interesting plot here. This is the total number of Bitcoins that actually exists. And so this over here is in millions. So here over here is 12 million. This goes up to about 22 million number of Bitcoins. The year here is 2009 when Satoshi first started. And because they're being generated each time people verify a transaction, this is going to increase. And actually going to increase around 2035. They estimate there'll be about 22 million Bitcoins. And it's actually slowly decreasing with time. And at some point, actually, there'll be no more creation of new Bitcoins. If you want to know how often these are used, this is a plot of the confirmed transactions per day for Bitcoin. And again, it started off pretty low down there around 2009. Here I'm at 2020. And what we've got is around 350,000 transactions per day that people are going ahead and giving each other Bitcoin. Again, it's pretty volatile. It's actually correlates a little bit with the price of Bitcoin. But 350,000 sounds like a lot. Unless you compare to maybe Visa. Visa actually produces 150 million transactions per day, a whole lot more. And one of the reasons is actually this verification process is somewhat slow, and this is a common criticism of Bitcoin. So here we go. Now we've gotten to the program that you're going to write. You're going to write a recursive program that creates a Merkle tree. And so here's what your program is going to do. It's going to read a vector of strings from input, and this is actually in the template file. So there's going to be a whole list of input strings that kind of represent what transactions would be. Your program is going to duplicate the last line if there's an odd number of lines of text. So you have to determine whether that is. Then what you'll do is you'll hash each line of text. And what you'll do is use the SHA-256 library. This creates that 256-bit hash, so you don't need to write the hashing function itself. This is included as a library file. It's included within the template file, so you don't need to worry anything about using it. Then what you'll do is remember you'll concatenate pairs of hash strings after you've hashed them, and then you're going to hash the concatenated string, and this is where the recursive part comes in, because you keep hashing, pairing, and you do that until you have only one hash left. That's called the Merkle root. So just a little bit of things. Remember, here's my Merkle tree. You've got all these lines of text that are read in from the screen. Again, you're going to go ahead, create a hash of that, and then you're going to concatenate them together, all until you end up with this one single hash at the top. That's the Merkle root, and your function is going to return that. Okay. Hashing, as I said, we'll use this library, so you don't need to write it. It's really simple. To do this, you're just going to write, this is the function call, SHA-256. You give it a single string, so this might be line 1 is a string, and it's going to return a single string. So it's very simple to go ahead and write the function that creates the hash. When you want to concatenate strings, if you remember, concatenation is very simple. You just use the plus sign. So maybe you had your 3 strings, hash 1 and hash 2, and then you had you wanted something to store your concatenated hash. You would just say simply hcat is hash 1 plus hash 2. And to go ahead and to use this SHA-256 library, as I said, there's this header file you need to include. We'll talk a little bit more about header files next week. But you go ahead and have this include statement. This is already in the template. You don't need to do it. This tells you this tells your program how to use SHA-256. And then again, now you can go ahead and use that function. You'll need to define the strings as variables, but that function will exist for you. So here's the template file. It's included in the Zybook. Again, there's my include statements, and notice up here at the top, there's that SHA-256 that's included. The first line is actually just the function prototype, so you don't do anything there. So it says don't write your program there. Here's my main program. Main program is very small, and you won't be modifying this either. This line right over here reads in a line of text strings. This is already done. It stores it in a vector of strings, which is called TXNS, short for transactions. And then there's a single line over here. Notice that this main program only has 2 lines of text. It outputs the Merkle. So this is going to be the program, the function you're going to write. And you go ahead and you send it to transactions. It's going to return a single 256-bit hash. You'll write it as a hexadecimal to the screen to go ahead and output it. So then down here is where you're going to write your function. So the template has the top line, which is how it calls. The function's called Merkle. It takes a vector of strings called D1, and then it's going to return a single Merkle root. And you're going to need to go ahead and add functions material right down in there. All right, let me just, one last thing, I'll just kind of give you an example if you feel maybe a little confused on how this goes. It's really not as hard as you might think. All right, so imagine your program reads in this vector of strings. There's a whole bunch of lines of text, and maybe those are what they are. Your program is then going to go ahead and hash each one of those lines of text. All right, so it's going to create it. It does it with that function, SHA-256. So you apply all this in a vector, so you can go just use your @ function in the vector, and this is going to output what the hash is. And then you go ahead and you concatenate them together. So you just use the plus symbol on those 2 strings. And then you're going to go ahead and take pairs again, and then go ahead and create a hash from it, again, using this SHA-256 function. But now what you're doing is hashing this line of text right over here. You can go put in any side of text that you want into there. And remember, you keep doing that until you're going to have one 256-bit hash. So maybe this is the last one that's paired together. You hash it, and then you're all done. You can see how this is repetitive, and this is why this is recursive. It's kind of calling in on itself, and this is why it's important to write this as a recursive function. It makes it very, very efficient. One last thing I mentioned in here, what happens if you have an odd line of text? So maybe what was read in, you have 1, 2, 3, 4, 5 lines of text, and you can't pair everybody up. And the protocol for that is go ahead and just repeat the last line of text. So then you would end up with 6, and then you can go ahead and hash and pair those together and go ahead and add this into your Merkle tree. So that's one last thing that you'll need to do. Okay. This may sound intimidating, and it's got a lot of interesting background, but it's not hard at all. You want to think this through, and in fact, this program can be written, you can write this in less than 10 lines of text. It's really not that difficult once you spend some time to think about it. So don't be intimidated from writing this program. Okay. All right, well, hopefully that background helps you out. Good luck this week. See ya.